Hello everyone, this is our next video for structure of atom chapter 2. In the previous videos we have discussed a lot about energy, radius, velocity, etc. To understand the atomic spectra or the atomic energy or the electrons, revolution of electrons in different orbits, what are the speed of electrons in different orbits, what are their distance from the nucleus from different orbits, etc. Today we will discuss about atomic spectra. Basically there are two types of atomic spectra: emission spectra and absorption spectra. Emission spectra, as I have discussed in the radius calculation. What is emission spectra? If a substance absorbs energy in any form, the electrons of that substance from the ground state moves to the next excited state. If the electron is present at this state, if it is electron and it is present at this state, it is called ground state. And after absorbing an electron, a substance, simply we take a substance that has absorbed energy, which already has some energy, and it moves from the ground state to the excited state. It moves from, by absorbing this energy, it moves from this state to the excited state. Already it absorbs energy and moves to the excited state. Then, it is not always present at excited state. It needs to come to the ground state. And when it comes from excited state to the ground state, it radiates some energy in the form of, and we adjust the apparatus prism to attract this energy, and after getting through the prism, this radiation give spectral lines. These lines are, moreover, it is continuous with very small black bands. I repeat, when a substance which absorbed energy, the substance is already, we are not giving energy to the substance. But if a substance has energy and it moves from the ground state to the excited state, either 1, 2, either 2, 3, if it is hydrogen, it is present if the ground state is first orbit, it jumps from first orbit to second to third, or from 1 to 3, whatever. But when it moves from excited state to the ground state, it radiates energy, and the spectra of that radiation is almost continuous spectra, called continuous spectra. Continuous spectra means if a white light is passed through the prism, you get an spectra, seven spectral lines. This type of radiation is called, this type of spectra is called continuous spectra. And when this emission spectra is almost continuous spectra with very few lines, black lines, which are absorbed by that element. If it is hydrogen, it absorbs some energy and that energy is not reflected here. This is black bands present in the spectra. So the spectrum of radiation emitted, this is emitted by the substance that absorbed energy, that has absorbed energy, means it already has some energy and it radiates energy. This type of spectra is called emission spectra. Our atomic spectra, each and every element has a unique emission spectra, or that type of spectra is its blueprint, or we can say that that type of spectra is fingerprint of that spectra. This type of spectra is fingerprint of an element. Many elements are discovered by this method. Helium is present in the sun, was discovered by the method, by this method, as when white light is passed through the prism and it gives some spectra. That spectra is of helium. So we can detect element by this emission spectra. Which element is present in the newly found substance? We can know the fingerprint of that element, and we can get the that element, that sodium is present, or chlorine is present, or magnesium is present in this substance by using spectroscope. Using spectroscope, we can get this. Second is absorption spectra. What is absorption spectra? If we are going to discuss the absorption spectra, this is like photographic negative of emission spectra. If emission spectra gives these several lines of dark band, then absorption spectra has more dark bands. If it is absorption spectra, then only colorful bands are very few and dark bands are much more here. These are dark bands, and in the dark bands only some spectral lines are present. By detecting that lines, by detecting the fingerprint of that lines, we can get the element present in it. So when a white light in this for getting this type of a spectra, a white light is passed through a tube. White light is passed through a tube. If it is hydrogen gas, then a white light is passed through a tube, and then this white light, then this gas radiates some energy, and by this radiated energy is passed through a split present in it. Some radiation is passed through the split, and in the spectroscope there are prism and prism, and by the dispersion of these lights we get the absorption spectra, like absorption spectra. Absorption spectra in which there are a broad black lines with some bright colored lines, colorful lines. So what is absorption spectra? When a white light is passed through a tube containing vapor or solution of a substance, some radiations are absorbed. Here some radiations are absorbed. These radiations, these white light radiations, these radiations are absorbed by the hydrogen gas, and the spectra we found is the spectra of the hydrogen gas. Like some radiations are absorbed by the substance, then the transmitted radiation obtained has some dark bands due to the absorption of these lights in hydrogen by the hydrogen gas. There are some dark bands are present in that type of spectra, and this type of spectra is called absorption spectra. So, what are the differences between the emission spectra and absorption spectra is a common question. Next is atomic spectra. Atomic spectra of hydrogen. As we know, when hydrogen gas absorbs energy and emitted some type of radiation, means when hydrogen atom, if we consider hydrogen atom, when hydrogen atom is at ground state and jumps to the excited state. If it is ground state and it is excited state, there are many excited states present in this in an atom. If the ground state, the excited state is up to R is equal to infinity, infinity से पहले तक. If the ground state is G, if it absorbs energy from this state to this state. If it is N1, it is N2, N3, N4, N5. It radiates energy to reach to the ground state or reach to the second state or reach to the third state or reach to the fourth state, etc. This type of radiation is this type of spectra is first observed by Barger, and he observed that hydrogen spectra have some lights, a type of spectra present in the hydrogen spectra, which is present in the visible region of electromagnetic spectrum. If it is at the ground state, the atom is present at the ground state, it absorbs. For hydrogen spectrum, if it is n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, and so on up to the infinity, n equal to infinity. If it jumps from the first excited state, it is ground state and it is excited state. From first excited state to the ground state, energy radiates is energy of ES minus energy of GS, ground state. So E2 equal to minus 13.6 Z square by N square, and E1 equal to minus 13.6 Z square by N square. If it is N2, then it is N2 square, and if it is E1 is N1, E1, so N is 1 here. So difference in energy means E2 minus E1. Difference in energy means E2 minus E1 is equal to delta E, which is equal to minus 13.6 Z square by N2 square minus 13.6 into Z square by N1 square. So minus here, this minus and this minus is equal to plus. So it is, we can write as 13.6 common, Z square it is also common, and it is now 1 by N1 square minus 1 by N2 square. So delta E equal to minus Z square, 13.6 Z square, 1 by N1 square minus 1 by N2 square. It is like that. If energy between these two, ground state and first excited state, the energy between these two, if the energy of the excited state is suppose it is 4 and it is the ground state energy is 2, the difference between these two is 2. Likewise, the energy difference between these two is this. We know that delta E equal to hc by lambda. We know that from E. So E equal to hc by lambda. For lambda, it is now Z square 1 by N1 square minus 1 by N2 square. Next, 1 by lambda, we need to calculate the wavelength. So 1 by lambda equal to 13.6 Z square by hc, 1 by N1 square minus 1 by N2 square. Or we can write 1 by lambda square is equal to wave number. This is wave number. 1 by lambda square, as we know, 1 by lambda square is wave number. Wave number is reciprocal to lambda. So wave number is equal to, and after calculating 13.6 H and C, we have a constant called Rydberg constant, Z square 1 by N1 square minus 1 by N2 square. And the value of Rydberg constant R is called Rydberg's constant. And the value of Rydberg constant is 1097 into 1097, or you can write it 109677 per centimeter, or 1.09677 into 10 to the power of 7 meter. This is the value of Rydberg's constant. By this value, we can calculate the lambda or wave number of the electrons. So in the hydrogen spectrum, the first time the spectrum is given by the Balmer, as mentioned, that Balmer was the first to mention the series of spectral lines. If light is passed through the hydrogen gas, which is placed in a tube, and then a beam of light is passed through the prism, spectral lines are observed. Which spectral lines are observed? These lines have definite pattern, definite number of spectral lines, and these lines are in visible region. These lines are in visible region. Hydrogen obtained from various sources. The spectral lines present in this type of spectra is always constant, always same. Hydrogen gas always give the same spectral line. Means the emission spectra by the hydrogen gas is always same. And there are some lines present in the spectra, which is called, first given by Balmer, then other scientists also give the spectra. Because it is visible in visible region, so the spectral lines which are present in infrared region or ultraviolet region are not given by the Balmer, given by the different scientists. The first line is called Lyman series. It is n equal to 1, it is n equal to 2, n equal to 3. These are n equal to 4, n equal to 5. As we go up, the difference between the lines becomes minimum, and at last n equal to infinity. First, if electron jump from second state n2 to n1, this occurs in Lyman series, and next n3 to n1, n4 to n1, n5 to n1, and so on up to the infinity. For Balmer region, Balmer series, the spectral line moves from second, third to fourth to second, fifth to second, sixth to second, likewise. For this is Lyman series, for Lyman series. This is for Balmer series. Next is from next series is for third and fourth. If electron moves from fourth to third series, fifth to fourth, fifth to third, sixth to third, Balmer series, then Lyman series, Balmer series, then Paschen series. Paschen series. After Paschen series, it is bracket series from 5 to 4. 5 to 4, 6 to 4, 7 to 4, likewise. This is called bracket series. Bracket series. And last is fund series. Other series are also present, but this is the last fund series. 6 to 5, 7 to 5, 8 to 5, etc. This is called fund series. P fund. This is called fund series. So there are 5 spectral lines, 5 types of spectral lines present. So for Lyman, Balmer, Paschen, bracket, and fund series, N1 and N2 are. What is the value of N1 and N2? So for Lyman, Balmer, Paschen, it is 1, 2, 3, 4, 5. And for Lyman series, it is start from 2, 2, 3, 4, and so on. For Balmer, it is 3, 4, 5. It is for Paschen, it is 4, 5, 6. And for bracket, it is 5, 6, 7, etc. For fund, it is 8, it is 6, 7, 8, etc. Sometimes in your question, what is the minimum number of N2 in Lyman series? It is 2, and for Balmer it is 3, and for it is the minimum number of N2 in these series, and the maximum number is infinity for every series. It is infinity for every series. Now, on the basis of these series and these spectral lines, there are scientists Zeeman and Stark. Zeeman and Stark. There are these scientists scientist Zeeman arranged magnetic field in line spectra and showed that there is a splitting off according to the Zeeman. This is deviation from the Bohr's model. According to the Zeeman's effect means Zeeman's magnetic effect. Splitting off spectral line in the presence of in magnetic field. When magnetic field is applied to the spectral line, there are further splitting of that spectral lines. So this theory is called Zeeman's effect. And for Stark, Stark told about the splitting of a spectral line in electric field. So we can write Stark effect like splitting of spectral line in electric field. So these are the deviation from the Bohr's model. These are the defects of the Bohr's model. Bohr's theory gives the spectral line or the spectra of for one electron system, not for the all electron system, all atom or all matter in the surrounding. Now next is dual behavior of matter. Dual behavior of matter. Niels Bohr said that Niels Bohr or other scientists like there is the dual behavior of matter. Not only dual behavior of hydrogen spectrum or any particular element or one electron system, there is a dual behavior of matter. Means matter acts as both as a wave and a particle. To prove this, de Broglie gave his equation by calculating Planck's energy equation, E equal to mc. Planck's is E equal to hc by lambda or E equal to h nu, and by Einstein it is mc square. By equating these two, we get hc by lambda is equal to mc square. Cc cancel. So we can get the lambda from here. If we calculate lambda is equal to h by mc. C here is velocity of light. C is velocity of light. If we compare the velocity of light, de Broglie change this velocity by v equal to h by mv. V equal to velocity of any matter. Velocity of any matter we can calculate by knowing the velocity of any matter. We can calculate the wavelength of that matter. So it is, we can write at lambda is equal to h by, this is p, P means angular momentum. P means momentum. So this is de Broglie equation for calculating lambda wavelength for any matter. Next is Heisenberg uncertainty principle. Before going to that, we can conclude that if electrons moves in this path, circular paths, and if it has wave-like motion, the wave formed by these electrons must be like this. Means it moves in the path that is MVR. The movement of the path is MVR, and we know that MVR is equal to NH by 2 pi. NH by 2 pi. Means if an electron start from here, it moves in this path, and finally when it reaches at this path, at this point, it again moves in this path. It again moves in this path. By this theory, we can calculate the uncertainty principle given by Heisenberg. So the next is Heisenberg's uncertainty principle. According to Heisenberg's uncertainty principle, it is impossible to calculate or determine simultaneously the exact position and momentum or velocity. Momentum by this momentum MVR or MV, and velocity. We can calculate the velocity by this momentum or velocity. It is impossible to determine simultaneously the exact position and momentum of an electron. If we calculate the position, it is denoted by x, and momentum of the electron is determined by p. The product of these two is always equal to or more than h by 4 pi, where delta x indicates position of the electron and delta p is momentum of the electron. Position and momentum of the electron. If we determine p, then if we determine x, then p becomes infinity, and if we determine p, x will becomes infinity. So this is the Heisenberg uncertainty principle. In the next video, we discussed about the quantum mechanical theory.